Okay, so I kind of changed my mind on the scheduling. Like, I just need to get over with some other things, and then we can learn some science. But one of my favorite topics or subjects is multivariable calculus. And hold up, there's a beeping noise. So okay, so that was an alarm. But multivariable calculus is one of my favorite subjects, or it's like the most interesting one, because we're no longer stuck to a plane. We're gonna look at the 3D world, and that's the most realistic world. So we're gonna study calculus in 3 dimensions. But before we get on the calculus part, we have to understand the 3D side first. Now, before we understand the 3D part, we have to learn about vectors. And this is what this video is going to be about. Now, because it's such a big subject and such a complicated one, I will have to go slow and just process things very slowly compared to my other videos. And I will have problems at the very end, that way people can actually understand and do the subject. So let's talk about vectors. And vectors are very useful. So there are two types of information, and they come in two groups. So the two types are the two types of quantities. There's a scalar quantity, and then there's a vector quantity. Now, the scalar is just any number. It really is just a number. Now, vectors give us two pieces of information. They give us that number, but they also give you a direction. And this is what this looks like. So there's different forms, but vectors give you a quantity and a direction. So if we were to describe a scalar, if we were visually to represent scalar, so the thing I want to really say is we can visually represent vectors because they give us directions and quantities. And the way we visually represent them is a segment, but with an arrow at the end of one of them. So this gives you the magnitude, the length of your vector, and it gives you the direction. So this is a vector quantity because it gives you the magnitude and then the direction. Here's an example of some bigger magnitude in a different direction. And that's another vector in a whole different direction with a different magnitude. Now, there's going to be so many terms and little tiny formulas that you'll get in multivariable. With vectors, it's just so much information being thrown at you at the same time. That's why I want to slowly process it. Vectors have magnitude and direction. Magnitude and direction. And the way we write this, I'll erase that one. So, you have your initial point, P, and then your terminal point, Q. We label this vector as any letter, I use V for vector, with an arrow on top of it. That's just saying it's a vector. Another way of writing a vector is by kind of putting together their initial and terminal points. So we can also write this as vector PQ. We can also write it like that. Either way is fine. So that's a takeaway. Okay. One thing I do want to bring up is kind of the terms. So, there are many types of operations we can do on vectors. We can multiply vectors, we can add or subtract them. Sorry. When I multiply, I mean multiply by a scalar, a number. And I'm going to demonstrate to you the operations and what they look. So with vectors, you know how with numbers, you can visually, I guess, represent what you're doing. With vectors, you always kind of want to visually represent what you're doing, because these operations have a visual purpose, as in like what you're visually doing with the vector. So I'm just saying gibberish right now, but it'll make more sense. So if we just decided to say, hey, if we had this vector v, and we want to multiply it by a scalar of 2, what you're going to do is you're going to have the same vector times 2. So this is 2 times the vector. So this is just the normal vector v. And then this is twice vector v. And you notice that the direction doesn't change. If you're multiplying by a scalar, your magnitude changes, but not your direction. And this would be 1/2 v, 1/2 of vector v. And the last kind of one that people get stuck a little bit on is this one. This one does change direction. It actually goes in the opposite direction. And this one's called negative vector v. So you're just swapping the direction. You're having the negative that vector. And these are the types of visual representations of scalar multiples. So these are scalar multiples. I'll leave that on the board. Okay. Let's say we had vector v and vector w, and we want to add them. We want to find out vector v plus vector w. We want to add them. Well, the way you visually do it is you take your first vector, you draw it, and this is the initial and terminal point. Remember the vocabulary words. And then you want to put vector w right, you want to slide it right on top where the initial points meet the terminal points of the other vector. So the initial point of vector w starts at the terminal point of vector v. So this is vector v and vector w. They're the same vector. I'm just sliding them. They mean the same thing. And then, to draw the sum of the vectors, the vector that equals the sum, you just start at the initial point of your first vector and go all the way to your terminal point of your last vector. And this vector right here is vector v plus vector w. That's what that equals. Now someone might say, well, what about if we do vector v minus vector w? Well, think about that as vector v plus the negative vector w. That might make it easier to visualize. So we still have positive vector v, but now we take, oh, this is negative vector w. We take the negative vector w. So this is vector v and this is negative vector w. And then we draw the vector, which is vector v minus vector w. And that's how you subtract vectors. So here are all the vector operations that we can do visually. These are very important to understand visually. You have to understand this. Scalar multiples. They're kind of like scaling the vector. These vectors are scalar multiples because they're multiplied by scalars. They never change the direction. And notice that scalar multiple vectors are parallel. That's a very important thing. So, okay. And it's just twice, 1/2, negative. It makes sense. And if you're adding, you're just taking the first and you're adding the second vector. You're drawing the sum of those. Easy. Now we're going to move on to what they look like graphically. I mean, more numerical notation. Okay. So, before we do this one, I want one thing to be extremely clear. Vector v This is exactly vector v. This is the same vector as this. Y has the same direction, has the same magnitude. It was just translated over. It is the same exact vector. It just translates. It was just translated. Translating a vector doesn't change it. It's the same vector no matter where it is. That's very important to understand. Okay, so if we have an actual graph, and we're going to draw a special vector. So if we translate a vector over to where its initial point starts at the origin, and I'll draw all the axes. And if I draw vector v, our famous vector. Wait, so if the vector's initial point is at the origin, then we can describe it numerically as, this right here, this distance is just the y value, right? It's the y value of this point right here. And this distance right here is just the x value of that point. So we can describe the vector numerically by using this special kind of vector where its initial point is at the origin. So there's different textbooks that call this differently. I like to call it these are called the components, and you'll see why. But this is v sub x. Some textbooks call it v sub 1. Others call it a. I don't care, but I like this one because it tells you that it's x. It's the x component. And this is the y component of the vector. So we could describe, hey, that's the distance that's the x value of that point, this distance, and this distance is the y value of that point. Wait, this is a vector and its initial point is at the origin. We can describe this vector numerically by putting these symbols right here, and v sub x comma v sub y, like that. They're inequality, they look like inequality symbols. They're not used for inequalities, but they're just inequality symbols. So hey, I can actually say that vector v equals this numerical description of a vector. Now this vector has a special name. It's called the position vector. Position vector. Kind of drew a line through it. I don't know why, but I was trying to underline that. So it's a special vector called the position vector, and its numerical description looks like that. There is another description using a matrix, and it looks like this. That's what it looks like using a matrix. Some textbooks use matrices. I don't like using matrices. I like using that notation. So So I will always be using that one. I will not use matrix as a notation. So, okay. Now there's another notation, and I'll tell you later, but before that let's go over some operations. So hey, if V sub, oh wait. What would W? What would W be? Will it be W sub X comma W sub Y? Okay. What if we wanted to add the vectors? Well, turns out the sum of the vectors is just the sum of their components. And same with subtraction. So plus or minus would work the same way. If we wanted to scale vector V with any sort of constant, that would be the constant times its components. It would look like that. So those are some operations. And then we can go over one more type of thing, and that's finding the magnitude of a vector. How large is this quantity? How long is this quantity? Wait, we know this. We know how to do that. Hey, this is a right triangle. What allows us to find the hypotenuse of a right triangle knowing these sides? The Pythagorean theorem, right? So, wait. The way we notate magnitude of a vector is we do like a double absolute value kind of thing. We do that. And that's called magnitude of vector V. That's how you pronounce it. Magnitude of vector V equals, wait, Pythagorean theorem says, hey, this side squared equals this side squared plus this side squared. If we solve for the magnitude, or the magnitude of vector V is going to be the square root of the sum of the components squared. The sum of the squares of their components. So that's the magnitude. That's your magnitude. It should make sense because it's a right triangle. Now, there's one more notation, and before we introduce it, we gotta cover other types of vectors. And, it's a lot of stuff to cover. So, let's talk about unit vectors. Unit vectors. What is that? Unit vectors are vectors with the magnitude of 1. So all unit vectors have a magnitude of 1. And the general, just like the general symbol for a vector is V with an arrow, the general kind of notation or symbol for a unit vector is a U with a little caret kind of thing on top. And that symbolizes that, hey, we have a unit vector. So that means, hey, we have a vector with unit length, with unit magnitude, a magnitude of 1. And the way you find the unit vector of every vector is, hey, if we have just a random vector and we want to scale it down to its unit vector, we just divide by its magnitude, because it has a magnitude of this, whatever it is. If you divide by it, you get a magnitude of 1. Dividing the same number by itself gives you 1. So the unit vector of any vector is the vector divided by its magnitude. And that's the definition of the unit vector. Okay. That's the definition of the unit vector. That's how you get a magnitude of 1 off of any vector. So that's how you scale the vector down to its unit vector. That's how you do it right there. I don't have that much time left, but I'm going to quickly show you the other notation of vector using our little knowledge of unit vectors. So if we take a look at its components, well, its components are really this vector and this vector. And notice that this vector plus this vector equals our actual vector. So wait. If we scale this vector down to its unit, we get this vector. And we have a special name for that. And if we scale this vector, the y vector, the y component of this vector, to its unit vector, we get another special name for that. And these vectors are called standard unit vectors. Kind of forget all these ones, the names. But the standard unit vector looks like this. So I put an I. So there's I. That is a standard unit vector, this unit vector. The I unit vector is, let's see, 1, 0, and the J unit vector, standard unit vector, is 0, 1. Now, wait. In the next video, because I'm running out of time, I'm going to talk about why these vectors are important in describing another notation for your vector. And I'll just do a bunch of problems, and then you could do one yourself.